You do not live in a crowded universe. You live in a universe that is almost completely empty, and that is not an exaggeration. Almost everything you care about, your body, your city, your planet, your star, is crammed into a tiny fraction of space, while the rest is basically nothing. Once you see the real numbers, the normal picture you have in your head of a bright, busy cosmos falls apart fast. Start with what feels full to you. You walk outside, you see streets, buildings, cars, lights. Your senses tell you this is a packed environment. This is normal density. Earth holds about 8 billion people on a sphere just under 8,000 miles across. That sounds huge, and from ground level it looks endless. But you live on a very thin shell of that sphere, just a few miles of atmosphere and a thin solid crust wrapped around a much larger ball of rock and metal. Even here, where life is dense, most of the planet is empty rock, empty water, and empty air compared to what is coming next. Now zoom out one level, to the solar system. Here, the idea of crowded breaks completely. Use a simple scale. If the sun were the size of a normal front door, Earth would be a pea, sitting about 220 feet away. That is more than half a football field. Between that door and that pea, you do not have a continuous fog of rocks and dust. You have almost total vacuum. The other planets are even farther. Jupiter would be another small object, hundreds of feet farther out again. You could move a solid object in a straight line through the inner solar system for millions of miles, and the odds of hitting anything bigger than a grain of sand are close to zero. That is what our neighborhood really looks like. A huge, dark volume with a few tiny objects scattered inside it. Your life exists on one of those small objects, hugging a narrow atmosphere, clinging to the surface, while almost all the space around you, even inside your own star system, is almost pure emptiness. So you might say, fine, the solar system is sparse, but a galaxy, that glowing band in the night sky, that has to be packed, right? Billions of stars, spiral arms, gas, dust. It has to feel like a city from above. That's the next illusion that breaks. The Milky Way is about 100,000 light years across. In miles, that's roughly 600 quadrillion miles. Your closest star neighbor, Proxima Centauri, is about 4 light years away, around 24 trillion miles. On a different scale, if you shrank the sun down to a ping pong ball, the nearest similar star would be another ping pong ball sitting several hundred miles away. Between those two balls, again, almost nothing. Space is not a tight star field. It's a huge volume where stars are extremely far apart, with very low average density. And our position inside that galaxy is not even in a relatively dense area. The sun sits inside something called the local bubble, a low-density region in the Milky Way, roughly 1,000 light years across. It was likely carved out by multiple supernova explosions in the past, which cleared and heated the interstellar gas. So inside an already sparse galaxy, you live in a carved-out, thinned-out cavity. The pattern keeps repeating. Every time you zoom out, the real content takes up less and less of the available space. At this point, you might remember the famous Hubble Deep Field images, those pictures where every point of light is a galaxy. Those images look like the universe is crammed with structures. Astronomers pointed the Hubble Space Telescope at a patch of sky that looked empty, about the size of a grain of sand held at arm's length, and after a long exposure, thousands of galaxies appeared in that tiny area. Later, even deeper observations pulled out around 10,000 galaxies from similar tiny patches. That sounds like the opposite of empty. Thousands of galaxies in a spot that small on the sky, scaled up over the whole sky, means hundreds of billions of galaxies in the observable universe. So where is the emptiness in that picture? It's hiding in the volume, not the surface. Each one of those galaxies is like the Milky Way, or smaller, or larger. But in almost every case, the stars inside are separated by light years of open space. Between those galaxies are even larger stretches of space, tens of millions, sometimes hundreds of millions of light years across, with almost no galaxies at all. Now look at the average. Take a cube of space, 1 yard on each side, often the middle of nowhere between galaxies. On average, you get only a few atoms of normal matter in that entire cube. Not molecules, not chunks of dust, just individual atoms. Compare that to a cubic yard of air in your room. That same cube of air holds something like 10 million trillion molecules. So the ratio is insane. What feels thin to you, like outer atmosphere or high-altitude air, is still unbelievably dense compared to the average density of the universe. Space is closer to perfect vacuum than anything you will ever experience on Earth. So, why is it like this? Why is the universe so committed to being empty? Why not more gas, more stars, more planets, more material everywhere? The key point, and this is the first really uncomfortable idea, is that if the universe were much denser, you probably wouldn't be here at all. If you fill space with more matter, gravity gets stronger on large scales. Stronger gravity doesn't politely give you more galaxies, it makes everything collapse faster. Big regions would pull themselves together quickly, forming huge clumps, black holes, and unstable structures. Stars would burn through their fuel faster, explode more often, and flood nearby space with lethal radiation. You wouldn't get long, quiet stretches where a planet can sit at a comfortable distance from a star, in a stable orbit, letting chemistry run for billions of years. What actually happened is a balance. The universe started hot and dense, then expanded and cooled. Tiny initial ripples in density, slightly more matter here, slightly less there, allowed gravity to pull material together into galaxies and clusters. But the overall density kept dropping as space expanded. That drop is not a side effect, it's the main protective feature. Low average density means galaxies can exist without merging constantly. Stars can sit far apart. Planets can orbit without constant disruption, and radiation from violent events doesn't sterilize everything all the time. So emptiness is not just the background detail of the universe, it's the platform that makes everything else possible. You only get galaxies, long-lived stars, and stable planetary systems in a universe that is mostly nothing. You are not tolerated because the universe is generous. You're tolerated because the universe is thin and stretched and quiet on average. That sets up a deeper question, and this is where the tension starts to climb. If almost all of space is empty and matter is only allowed to exist in rare, thin structures, how exactly is that matter arranged on the very largest scales? Is it just random, a mist of galaxies? Or is there a pattern that shows you what gravity and time have really done to the universe? When astronomers finally built full 3D maps of where galaxies actually sit in space, and not just where they appear on the sky, they found something that looks less like a cloud and more like a skeleton, a web, with almost all the matter locked into thin lines and nodes, and gigantic regions of almost pure nothing in between. So when astronomers finally mapped where matter actually is, what did they see? Not a smooth fog of galaxies, not a random spray, but a structure that looks almost alive. And the first punchline is this: almost all of it is still void. For a long time, we only had flat maps of the sky, just positions of galaxies as dots on a dome. That tells you where they appear, but not how far away they are. The real change came when big surveys like the Sloan Digital Sky Survey and the 2DF survey started measuring redshifts for huge numbers of galaxies. A redshift is basically how much a galaxy's light is stretched by the expansion of the universe, and from that stretch, you can estimate distance. Once you have millions of distances, you can turn the sky into a 3D map. Now, here's the weird part. When you plot those galaxies in 3D, you do not get a uniform cloud. You get a pattern. Long, thin filaments, walls, and at the intersections, big clumps where galaxy clusters live. Between those structures, you see enormous hollow regions with almost nothing in them. That whole pattern is what we call the cosmic web. Galaxies are not just out there randomly. They ride along these invisible lines of matter, like beads on threads, while most of the volume between those threads is basically empty. How empty are those gaps really? The hollow regions, the cosmic voids, are huge. Typical voids can span 100 to 300 million light-years across. That is a region so large that you could fit thousands of Milky Way-sized galaxies inside it and still have room left over. But in reality, you might get just a handful of small galaxies, or almost none. On a raw volume count, these voids dominate. If you pick a random point in the universe, the odds say you are in one of these underdense zones, not next to a galaxy like the Milky Way. So how do you end up with this strange skeleton, with matter clinging to thin lines and almost abandoning the rest? Is this some kind of special design, or just a side effect of simple rules running for a long time? The answer is harsh and simple. This all comes out of basic gravity plus the initial conditions of the early universe. When you look at the cosmic microwave background, the leftover glow from the early universe, you see tiny fluctuations in temperature and density, slightly hotter spots, slightly colder spots, slightly more matter, slightly less. Those differences are tiny, but gravity does not treat them equally. Regions that start out a little denser pull in more matter. As more matter falls in, their gravity gets stronger. They pull in even more, and they grow into the filaments and clusters we see today. Regions that start out slightly less dense lose matter to their neighbors, and over time, they get more and more empty. That is a brutal rich get richer effect written in physics. Once a region is a little ahead, it keeps gaining. Once a region is a little behind, it keeps losing. Over billions of years, matter is literally sucked out of the voids and funneled into the filaments and nodes. The result is that the universe evacuates most of its volume, shipping its contents into a small fraction of space and leaving the rest as deep, cold nothing. If that sounds abstract, there's a concrete example that shows how extreme this can get. What happens if you end up inside one of the biggest voids we have found? One of the most famous cases is the Boötes void. It sits in the direction of the constellation Boötes, and it's roughly 330 million light-years across. That distance is so big it's hard to feel, so focus on the ratio instead. In a region that large, if galaxies were spread more evenly, you would expect thousands of bright galaxies. Instead, in this whole enormous bubble, astronomers have found only a few dozen reasonably bright ones. Think about what the sky would look like from the middle of that thing. In our region of the universe, when you look with a big telescope, you see a decent number of galaxies scattered across the sky. From the center of Boötes' void, you would see far fewer galaxies, and they would be clustered in just a few directions. Huge stretches of sky would be almost blank. You wouldn't just feel like you're in the countryside instead of the city, you would feel like you're parked on the edge of reality itself, with nothing in most directions for hundreds of millions of light years. And Boötes isn't a one-off freak. Catalogs of large-scale structures show voids everywhere. Big ones, smaller ones, nested ones, forming a hierarchy of emptiness that spans a huge fraction of the universe's volume. Statistically, if you could teleport to random coordinates in the cosmos, you'd probably land in a void, far from any bright galaxy, and the nearest real structure would be unimaginably far away. So here's the next disturbing question. Does this web structure smooth out over time, like ripples calming on a pond? Or does it get even more extreme as the universe ages? The unsettling answer is that the web doesn't relax, it sharpens. As time goes on, gravity keeps doing what it's always done, pulling matter along the filaments into clusters and superclusters. The regions that are already dense keep getting denser. The voids, already underdense, keep losing what little matter they still have. Once a region has been drained into a void, there's no mechanism that brings fresh matter back in. Expansion of the universe stretches everything, but it doesn't refill the gaps. That leads to a kind of lock-in. On the largest scales, the pattern you see now, filaments, nodes, and voids, is not heading towards a smooth blur. It's heading towards a future where the bright parts are more sharply separated, and the empty parts are even emptier. Over very long times, isolated clusters of galaxies become the main islands of matter, while the voids become almost perfect vacuums. So you're not living in a universe that's evening out into some calm, uniform fog. You're living in a universe that's already committed to being a small, connected network of bright islands surrounded by a sea of almost pure nothing. And that contrast is only going to get stronger. Which raises the next problem. If matter is trapped in a web, in a small fraction of space, and most lines of sight cross huge voids before hitting anything, why is your night sky not just a solid wall of light from all those stars and galaxies stacked along your view? If the universe is full of stars and galaxies, your night sky should be blinding. Every direction you look, your eyes should slam into starlight. The fact that you see mostly black with a few tiny dots is not comforting. It is a warning about how the universe is really built. There is an old question called Olber's paradox. Take a universe that is infinite, goes on forever in space, and has stars spread out more or less evenly. In that kind of universe, every line of sight should eventually land on the surface of a star. The details of distance do not save you because distant stars are dimmer, but there are more of them. Add everything up, and the sky should glow like the surface of the sun. No darkness, ever. You should not be able to sleep under that sky. But you do not see that. You walk outside at night, away from city lights, and the sky is mostly empty black, with just a thin dusting of stars and, if you are lucky, a pale strip of the Milky Way. That mismatch is the paradox. If the cosmos is so full of stars and galaxies, why is the sky not a solid wall of light? The resolution comes from three hard facts about the real universe. First, it is not infinitely old. It has a finite age, around 13.8 billion years. Second, it is expanding. Space itself is stretching, changing the distances between galaxies over time. Third, as you have already seen, most of it is empty, with matter confined to thin structures and islands. Put those together and the dark sky suddenly makes sense in a very uncomfortable way. Start with the age limit. Light does not arrive instantly. It has a finite speed, about 186,000 miles per second. That's fast, but not infinite. When you look at a galaxy 10 billion light years away, you're not seeing it as it is now. You're seeing it as it was 10 billion years ago when the light left it. Anything farther away than roughly 13.8 billion light years in light travel distance simply has not had enough time to send light to you, because the universe itself has not existed long enough. That means you live inside what's basically a growing light bubble. There is a sphere around you in all directions, and only sources inside that sphere have had time to light up your sky. Outside that sphere, there can be galaxies, clusters, collisions, even entire regions full of activity, but none of their light has reached you yet. For you, they might as well not exist. Your visible reality is a subset of the total universe, limited by how long light has been traveling since the Big Bang. And that subset is not fixed. It grows with time, as more distant light finally reaches you. But this does not mean you are running toward a future where the sky fills up and becomes bright. Something else is happening at the same time that fights against that growth, and in the long run, wins. This is where expansion and redshift come in. The universe is not static. Space itself is stretching. As light travels through this stretching space, its wavelength gets stretched too. Shorter wavelengths, like blue and ultraviolet light, get stretched into red. Red gets stretched into infrared. Infrared gets pushed into microwave. That shift to longer wavelengths is what we call redshift. You see one extreme example of this already. Right after the Big Bang, the universe was filled with hot, bright radiation. Over time, as space expanded, that radiation cooled and stretched. Today, you still see it as the cosmic microwave background, a very faint glow at a temperature just 2.7 degrees above absolute zero. It started as intense, almost white-hot light. Now it's a cold, low-energy radio whisper. The same process is hitting light from distant galaxies. The farther away a galaxy is, the more the expansion of the universe has stretched its light by the time it gets to you. For nearby galaxies, the shift is small, and you still see them in normal visible light. For very distant galaxies, the shift is huge. Their light is pushed into infrared or microwave bands that your eyes cannot detect. Even many telescopes need special detectors to pick it up. So even inside your light bubble, even among the galaxies that have had time to send light to you, a lot of that light is being dragged out of the visible range. The universe is literally hiding its own brightness by stretching it into wavelengths that your eyes and even some instruments don't see. Now add the third piece, emptiness. Most lines of sight from your eyes do not go straight to a star or even straight to a galaxy. They go through enormous voids, regions hundreds of millions of light years across that contain almost nothing. Only after passing through all that empty volume do they eventually hit a filament or cluster where galaxies live. That means most of your sky is not layered star on star on star. It's mostly blank space, with a few thin structures puncturing that emptiness at great distances. Put this together, and the dark sky stops being a mystery and starts being a diagnostic tool. The sky is dark because the universe has a finite age, so you only see out to a limited distance. It's dark because space is expanding and stretching light into low-energy wavelengths that barely register. It's dark because the matter that could make the sky bright is confined to a small fraction of the volume, with huge voids in between. In other words, the darkness itself is proof that the universe is mostly empty, that it's expanding, and that it hasn't been around forever. If any of those three facts were very different, your night sky would not be calm and dark, it would be lethal. Run the thought forward. If the universe were eternal, not expanding, and nicely filled with stars, the total brightness from all that starlight would build up until every square inch of the sky was blazing. The energy hitting Earth would be enormous. Your planet would not sit gently under a cool night sky. It would be roasted under a permanent all-direction radiation bath. Life as you know it would not have a chance. So, the darkness that feels peaceful is actually a sign that you live in a very specific kind of universe, one that is only temporarily friendly. The same expansion that keeps the sky from turning into a wall of fire is also slowly pulling galaxies away from you, pushing their light out of sight and cutting off parts of the universe from your reach forever. And here is where the tension really starts to climb. If expansion is the reason your night sky is dark and survivable, what happens when that expansion doesn't just continue, but actually speeds up until most of the galaxies you can see right now get erased from your future not by explosion, but by distance? Right now, you're watching the universe switch modes. It stopped focusing on building big structures, and it started focusing on pulling everything apart. That's not a guess. It's something we actually measured using exploding stars, and the result forced physics to accept a new invisible ingredient in the universe: dark energy. In the late 1990s, two independent teams of astronomers tried to answer a simple question: how fast is the expansion of the universe slowing down? The logic was straightforward. Gravity pulls matter together, so over billions of years, the expansion that started in the Big Bang should gradually decelerate, like a thrown ball slowing as it climbs. To measure this, they used Type A supernovae, very bright stellar explosions that behave in a predictable way. Type A supernovae act like standard candles. Their peak brightness is very similar from event to event. So if you see one and you know how bright it should be, you can compare that to how bright it appears and work out how far away it really is. Combine that with redshift, which tells you how much the universe has expanded since the light left, and you get both distance and expansion history in one shot. The teams pushed this method to large distances, billions of light years out, and that is where something broke. The distant supernovae were too dim, not a little bit, but systematically dimmer than they should have been in a universe that was slowing down under its own gravity. The only way to explain this cleanly was if those supernovae were farther away than expected, which means the universe has expanded more than expected, which means the expansion is not slowing down, it is speeding up. That single flip from slowing to accelerating is what gave us dark energy. To make the numbers work, you have to add a new component to the universe, something that does not clump like normal matter, that does not dilute in the usual way when space expands, and that has a kind of negative pressure that drives acceleration. Today, the best measurements say this dark energy makes up about 68% of the total energy content of the universe. Most of what exists is not matter, not radiation, but this smooth, invisible term that pushes space apart. So, what does an accelerating expansion actually do to your future, not just to your equations? The key effect is that acceleration creates a real horizon in space, a limit beyond which events are cut off from you forever, no matter how long you wait, no matter what technology you build. Because space is expanding faster and faster, there is some distance at which the expansion speed, the rate at which new space appears between you and a distant galaxy, outruns the ability of light to close the gap. If a galaxy is beyond that critical distance, any light it sends toward you now will never get here. It will always lose the race to the stretching of space. That distance defines a kind of cosmic event horizon, not a black hole horizon, but the same idea, a boundary of no return for information. Right now, that horizon is on the order of tens of billions of light years away. Objects that cross it are not physically destroyed, but from your point of view, they are gone, permanently removed from your possible future. Over time, as dark energy keeps driving the expansion, more and more galaxies slide beyond that horizon. The total universe keeps getting bigger, but the part of it that can ever affect you shrinks in terms of accessible matter and signals. So what about your local neighborhood? What stays and what is lost? The Milky Way does not sit alone. It belongs to a small collection of galaxies called the Local Group, which includes Andromeda and a few dozen smaller dwarf galaxies. This group is roughly 10 million light-years across. Inside this region, gravity is strong enough to hold everything together against the expansion of space. On very long timescales, the Milky Way and Andromeda will merge, and many of the smaller galaxies will be swallowed, forming one big remnant system. Outside the local group, though, the story is different. Galaxy clusters and superclusters farther away are receding from us because of expansion, and as dark energy dominates, their recession speeds, measured over the vast scales of space itself, become faster than the speed of light. That does not violate relativity because nothing is moving through space faster than light. The space in between is just growing. But the consequence is the same for you. Signals from those systems stop reaching you. Fast forward tens of billions of years. If dark energy keeps behaving the way it does now, every galaxy that is not gravitationally bound to the local group will redshift so much that its light becomes undetectable. From the point of view of observers living in that far future, only the merged remnant of the local group will still be visible. Everything else, all the filaments, all the clusters, all the other galaxies that you can observe today, will have disappeared into the darkness, not because they died, but because the universe pushed them out of reach. At that point, the universe turns into a collection of island universes, each one a bound group or cluster cut off from all the others by expanding void. For us, the prison cell is the local group. For some other civilization in another cluster, theirs is theirs. No one crosses the gaps. Dark energy is what makes this isolation permanent. Unlike matter, dark energy does not clump, it does not cool, it does not form structures. It fills space more or less uniformly, and as space expands, its overall influence grows. The more volume there is, the more total dark energy there is, and the more it dominates the behavior of the universe. Matter gets thinner as space stretches, but dark energy keeps driving the process. Over very long times, this has a clear effect. Densities drop, galaxies stop merging on large scales, interactions between distant structures become rarer, and the cosmic web you see today fades from a huge connected network into scattered, disconnected islands, each one hanging in an almost featureless vacuum. The big pattern remains in frozen form inside each island, but the links between islands are broken. So the universe is not just empty right now, it's actively investing in becoming emptier. It's pushing almost everything you can see today beyond any possible contact, while it stretches the gaps wider and wider. And while all of that is happening on the largest scales, something just as serious is happening inside those remaining islands themselves. Because even if you stay bound to your local group, even if gravity keeps your little patch of the universe together, the factory that makes new stars inside those galaxies is already past its peak and is slowly shutting down. You are not living in the universe's boom time, you're living in the slow decline after the boom. You probably feel like you live in a young, active universe, full of galaxies, full of bright stars, with endless time ahead. That picture is wrong. On the cosmic clock, you showed up late, in the declining phase. The universe already had its golden age of star formation, and that age is over. Astronomers can actually plot how fast the universe has been making stars over time. They look at galaxies at different distances and different redshifts, which means different ages, and measure how much new star formation is happening in each one. When you stack all that data, you get a cosmic star formation history curve. It is not flat. That curve peaks roughly 10 billion years ago. Back then, the universe was making new stars at a rate around 10 times higher than it does today. Galaxies were gas-rich, they were churning out bright young stars constantly, they were messy and active. Since that peak, the rate has dropped, not a little, but by a large factor. Today, the universe is much quieter. It still forms stars, but the overall production line has slowed way down, and the slowdown is continuing. Why? Because galaxies are running out of fuel, and what fuel is left is getting harder to use. In galaxies like the Milky Way, the raw material for new stars is cold gas, mostly hydrogen, sitting in dense clouds called molecular clouds. These clouds can collapse under their own gravity and form clusters of new stars. But those same stars, once they live and die, actively damage the fuel supply. Massive stars explode as supernovae. Those explosions pump huge amounts of energy into the surrounding gas, heating it up, stirring it, sometimes pushing it completely out of the galaxy's disk into a big hot halo. Supermassive black holes in galactic centers can do something similar. When they actively feed, they launch jets and winds that blow gas out of the central regions. Galaxy collisions can compress gas in some places, but they also fling gas into tidal tails and halos, where it is more diffuse and hotter. Once that gas is heated and spread out, it is hard for it to cool and fall back into dense, cold clouds. Cooling takes time, and in the meantime, gravity is weaker on that diffuse gas, so the galaxy's ability to make new stars declines. Over billions of years, a spiral galaxy can go from a blue, star-forming system to a more subdued, gas-poor system where only a trickle of new stars are born. You can see the end state in the big galaxies that already finished this process. In massive galaxy clusters, many of the largest galaxies are giant ellipticals. They do not have bright blue spiral arms. They have smooth, rounded shapes, and their light is dominated by older, redder stars. Astronomers call them red and dead, not because nothing is moving inside them, but because they have almost no cold gas left to make new stars. Their star formation has been quenched. When you look at the universe today, you do not just see a few of these fossils, you see a lot of them. Many massive galaxies shut down their star formation billions of years ago. They used up, heated, or blew out their gas, and now they just slowly age. That is the future of most galaxies, including systems like ours over long enough timescales. The universe is already full of these retired galaxies, and the fraction will only go up. So, what does a dying star field mean for life? New stars are the starting point for new planetary systems. Each new batch of stars, especially metal-rich stars like the Sun, can host rocky planets, some of which may sit in habitable zones, with liquid water and stable climates. If you lower the star formation rate, you lower the rate at which new planetary systems appear. Fewer new stars means fewer new chances for life to get started. Now, low-mass stars that already exist, like red dwarfs, will live for a very long time, far longer than the Sun. Some will burn for trillions of years, so the universe will not be empty of stars anytime soon. But the key point is this: the birth rate is collapsing. The stock you have now, plus whatever gets added in the near future, is basically it. You're watching the tail end of the big construction phase. You also depend on the chemistry that previous generations of stars created. Heavy elements like carbon, oxygen, silicon, iron, the stuff your body and your planet are made of, were forged in stars and supernovae. The era when the universe was most efficient at making both stars and heavy elements is behind you. You're living in the afterglow of that productivity, not the peak. So your situation is strangely narrow. You emerged in a window where the universe still has enough cold gas to build bright, metal-rich stars, enough ongoing star formation to produce complex planetary systems at a decent rate, and enough leftover radiation and energy gradients to power complex chemistry. That window is not permanent. With each passing billion years, the universe has fewer new stars, fewer fresh planets, and more red and dead regions. And remember what dark energy is doing at the same time. While star formation slows inside galaxies, dark energy is accelerating the expansion between galaxies. That means your supply of new stars is not only shrinking, the rest of the universe that might have had its own chances for life is being pushed away from you, locked behind a horizon you can never cross. So here's the next hard question. Even if you wanted to fight this trend, even if you built the most advanced starships you can imagine, could you actually reach all those other galaxies? Or even most of the ones you can see today? Do you have any real access to that fading star field? Or is something deeper in the basic rules of physics already cutting you off from almost everything? Even if you had the best starship you can imagine, the universe has already slammed most of its doors in your face. That's not about money or engineering or ambition, it's baked into the rules of physics. There's a hard speed limit, and then there's the even worse fact that the stage you're standing on is stretching under your feet. Start with the simple part. There's a cosmic speed limit, about 186,000 miles per second, the speed of light in a vacuum. Special relativity says nothing with mass can be pushed all the way to that speed, let alone beyond it. The closer you get, the more energy you need, and the cost blows up. Every experiment we've ever done, from particle accelerators to GPS satellites, fits this rule. No signal, no ship, no clever trick has ever been seen to move through space faster than light without breaking the theory that keeps modern physics working. So right away, that means there's a maximum pace at which you can cross distances. Even if you somehow build a ship that cruises at 99.9% of light speed and somehow keeps people alive and sane for hundreds of thousands of years, you still can't cheat the basic limit. You're stuck below that number. On human scales, 186,000 miles per second sounds insanely fast. On cosmic scales, it's slow. Now add the second layer, which is worse. The universe is expanding, and that expansion is not normal motion, it's space itself stretching. Galaxies are mostly not flying through space at huge speeds, they're more or less sitting in place, while the distance between them grows because the underlying fabric is stretching. Relativity's speed limit applies to motion through space, not to the rate at which new space appears in between distant points. So that means beyond a certain distance, even light emitted toward you right now will never make it to you. The expansion carries that light away, stretches its wavelength, and keeps adding distance faster than the light can erase it. So there are regions of the universe that aren't just far, they're fundamentally unreachable. Not unreachable because you're too weak or too primitive, unreachable because the geometry of space is changing in a way that always wins the race. This is where the difference between observable and reachable really matters. The observable universe is the region from which light has had time to reach you since the Big Bang. Because of expansion, that radius is not 13.8 billion light years, it is roughly 46 billion light years. That is your past light bubble, the volume that has managed to send you a signal in the age of the universe so far. But the reachable universe is smaller. That is the set of places you could aim a ship at today at sublight speeds, and in principle arrive someday, even if you wait trillions of years. Because of accelerating expansion, a huge fraction of the galaxies you can see right now are already outside that reachable set. Their light is reaching you today because it left long ago when they were closer and the expansion was slower. But light they emit now, in this era, is doomed never to arrive. So imagine what that really means. Most of the galaxies in those beautiful deep field images, the ones you see as faint smudges at the edge of detection, are not destinations. They are already ghosts. You are watching light that left them billions of years ago, from positions much closer to you than they are now, and on any future map of places we could ever visit, they do not make the list. Even in principle, even with perfect technology, they are gone. That is the cold version of cosmic isolation. Even at a science fiction level of engineering, you are trapped in a local neighborhood. Realistically, your cage is your galaxy group, maybe a bit more if you push things hard, but not the whole web, not the full set of clusters and filaments you can map. Other civilizations, if they exist in distant galaxies, are almost certainly in the same situation. They are locked into their own island, with their own local group watching the rest of the universe slide away from them too. The universe is not a big empire map waiting for some advanced species to paint it with colonies. It is a set of sealed city-states, each one a gravitationally bound region drifting apart forever in a darkening sea. Emptiness here is not just an accident, it is enforced at the level of geometry. The rules that control space and time themselves are pulling the actors away from each other, faster than they can ever run. So put this together with what you already know. The universe is mostly empty, the matter that does exist is locked into thin filaments and small islands, dark energy is pushing those islands apart, star formation inside them is already past its peak and fading, and the speed limit plus expansion means you can't even reach most of the remaining islands. You are boxed into a small temporary pocket of structure in a universe that does not let its structures talk to each other for long. The next question is, what is it like inside that box? If you are stuck in a local patch of the universe, unable to leave, how friendly is the space around you really? Because the bad news is, the tiny fraction of the universe that is not empty is not calm. It is full of explosions, radiation, and kill zones that carve away most of the places where life could safely exist. Space is not just empty. The small parts that are not empty are often straight up hostile to anything fragile. You don't just need matter and energy to get life, you need the right amount, in the right form, for a very long time without giant explosions wiping the slate clean. Once you look at what actually happens around big stars and black holes, you see how thin that safety margin really is. Start with supernovae. When a massive star dies, it doesn't quietly fade away. Its core collapses, its outer layers blow off, and in a few seconds, it can release as much energy as the sun will emit in its entire 10 billion year lifetime. That is not just a bright firework, that is a radiation event on a ridiculous scale. If you sit within a few dozen light years of a supernova, so within hundreds of trillions of miles, the effects can be lethal for a biosphere. Intense high-energy radiation can strip away ozone, break apart molecules in the upper atmosphere, and let hard ultraviolet light from the host star hammer the surface. Over time, that can trigger mass extinctions, collapse food chains, and basically reset whatever evolution was doing. You don't need to be right next door, you just need to be too close on the wrong day. Now, think about where massive stars tend to live. They form in dense star-forming regions and clusters, where you have lots of gas and lots of new stars being born together. Those regions don't just make one massive star, they make many, and those stars live short lives and blow up in sequence. That means some parts of a galaxy are no-go zones for long-lived biospheres. The radiation environment changes too often, too violently. You might get life starting, but it keeps getting interrupted, knocked back, or wiped out. And supernovae aren't even the worst thing the universe can throw at you. There's another class of event that is more focused and even more brutal: gamma ray bursts. Gamma ray bursts, or GRBs, are intense flashes of high-energy gamma rays that can outshine an entire galaxy for a few seconds to a few minutes. They're thought to come from things like collapsing massive stars with jets, or mergers of neutron stars. Whatever the detailed mechanism, the key point is simple. For a short time, they dump a huge amount of deadly radiation into narrow beams. If one of those beams passed over Earth from within a few thousand light years, it could dump enough energy into the upper atmosphere to break apart nitrogen and oxygen molecules, create nasty chemical reactions, and strip away large parts of the ozone layer. That can let extreme ultraviolet radiation from the sun hit the surface more directly, stressing or killing a lot of life, especially anything near the surface of oceans or on land. You can get mass extinctions from that kind of hit without ever seeing a physical impactor. Observations suggest GRBs are more common in certain kinds of galaxies, especially low metallicity, intensely star-forming galaxies, the kind you might expect early in the universe's history or in rougher neighborhoods. That's exactly where you might think first-generation life attempts would happen. Lots of stars, lots of energy, lots of chances. But they are also the places where the radiation environment is harshest and most unstable. The universe offers a big menu of new stars there, and at the same time, it aims high-energy sniper rifles at them. Move up another scale to the centers of galaxies and the early quasar era. Many galaxies, maybe most large ones, have a supermassive black hole at the center, with millions or billions of solar masses. When enough gas falls toward that black hole, it doesn't just disappear quietly. The infalling material forms a hot, bright disk, and magnetic fields can launch jets of particles out of high speeds out of the poles. An active supermassive black hole becomes an active galactic nucleus, or in extreme cases, a quasar. During those phases, the core of the galaxy floods its surroundings with radiation, from X-rays to ultraviolet, and with particles streaming out along jets. That output can reach across hundreds of thousands of light years. It heats gas, strips it, and batters anything nearby. In the early universe, quasars were more common because there was more gas around to feed central black holes. That means early cosmic time and the downtown regions of galaxies were even rougher places to try to build and maintain complex life. If you want a stable, low-radiation environment where a planet can sit quietly with a mostly steady energy input from its star and without constant catastrophic hits from above, you do not want to be too close to a starburst region. You do not want to be near a recent GRB, and you do not want to live near the core of a quasar-level galaxy. You want distance. You want to be in the quieter parts of the disk, away from massive clusters, away from the central engine. So add all of this up. There are zones in galaxies that are too violent, with too many massive stars blowing up. There are times in the universe's history when GRBs and quasars are more common and more dangerous. There are environments like dense clusters and galactic centers where the combined radiation, collisions, and gravitational chaos make long-term stability almost impossible. The result is a galactic habitable zone, a term astronomers use for the parts of a galaxy where conditions are mild enough, long enough, for complex life to have a real shot. Not too close to the center where things are crowded and violent, not too far out where there might not be enough heavy elements to build rocky planets and complex chemistry, not in the earliest epochs when radiation events are frequent, not inside the wildest clusters where close encounters are common. That zone is already a small fraction of the total volume of a galaxy. Combine that with what you already know, that most of the universe's volume is empty void, that only thin filaments hold galaxies at all, and that inside those galaxies only certain regions are calm enough for billions of years at a stretch, and you get a very sharp picture. The universe is not just mostly empty. Most of the places that are not empty are not stable, not gentle, and not suitable for complex life over long times. Habitability ends up being a razor-thin compromise between too much nothing and too much chaos. You need enough matter to build stars and planets, but not so much activity that radiation and collisions constantly reset the board. You need to sit in a quiet pocket, in a quiet time, on the right kind of world. Which raises the next question. If the safe zones are that thin and the conditions are that strict, how many actual planets pull off the full set of requirements? Because when we started finding exoplanets, it looked like planets were everywhere, and Earth-like worlds would be common. But the more we look in detail, the more filters appear, and the odds for a truly Earth-level setup start to look a lot worse than they did at the beginning. When astronomers first started finding planets around other stars, it was easy to jump to a simple conclusion. If planets are everywhere, Earth-like planets must be everywhere too. That would mean the universe is full of potential Earths, full of oceans, full of atmospheres, full of places where life could get started. But as the data improved, the story shifted. Planets are common, yes, but truly Earth-like setups look more and more like a rare outcome of a long chain of filters. Surveys like Kepler and TESS have stared at huge numbers of stars, measuring tiny dips in brightness as planets pass in front of them. From those dips, you can infer how many stars have planets, what sizes those planets are, and how close they orbit. The answer is loud and clear. Planets are not special. Many, maybe most stars have at least one. Estimates now suggest there are more planets than stars in the Milky Way. We are talking hundreds of billions of worlds, maybe trillions, just in this one galaxy. On the surface, that sounds like very good news. Hundreds of billions of tries at building something like Earth. Even if only a small fraction are in the right conditions, you still get a huge number of habitable worlds, right? That was the optimistic reading early on, but it leaned on a very rough idea of habitable. Basically, is the planet at a distance where liquid water could exist? That distance range around a star is called the habitable zone. For a sun-like star, it is a relatively thin band. A little closer in, and you risk a runaway greenhouse effect, where the planet heats up, water turns to steam, and the atmosphere traps more and more heat, like what happened to Venus. A little farther out, and you end up cold and frozen, like early Mars. So just on distance alone, you don't get a wide margin. You need a fairly tight orbit for surface water to stay liquid over long periods. When you look at real planets sitting in those zones, another problem appears. Many of them are not Earth-like at all. Around small, cool stars, it's common to find planets in the habitable zone that are tidally locked, always showing the same face to their star, with one side in constant daylight and the other in permanent night. That makes climate and atmosphere behavior much more complicated. In many systems, the planets in the right temperature zone are not true Earth-mass rocky planets, but gas dwarfs or super-Earths, with thick, crushing atmospheres or deep global oceans without continents. You can maybe imagine some forms of life in these setups, but they're not clean Earth copies. Then you have to look at the architecture of the whole system. The layout of your solar system is not obviously typical. Giant planets like Jupiter and Saturn sit far out, and their orbits are fairly stable. There's good evidence that Jupiter in particular played a big role in shaping the inner system. It likely ejected or deflected a lot of comets and asteroids that would otherwise have slammed into Earth and its neighbors. It's not a perfect shield, but without a giant planet out there, the impact rate on inner planets could have been much worse. Large moons matter too. Earth's moon is big compared to the planet. It helps stabilize Earth's axial tilt, which keeps the seasons within a certain range over long timescales. If the tilt wandered wildly, climate would swing harder, and long-term stability for complex ecosystems would be harder to maintain. The moon also drives tides that may have been important for early chemistry in shallow coastal regions. Many exoplanets we see don't obviously have big moons, and many systems have very different giant planet layouts. On top of that, exoplanet surveys have found many hot Jupiters, giant planets orbiting extremely close to their stars, with years that last only a few days. These giants probably didn't form that close in. They likely migrated inward from farther out. That migration would disrupt or destroy any small rocky planets in the inner system, or radically rearrange their orbits. In systems like that, even if a planet ends up in the habitable zone later, its history may have been chaotic and hostile. So when you stack these factors, the picture shifts from tons of Earths to tons of planets with Earth-like setups hidden in a small subset, and we're not done yet. To get something like Earth, you need a star with the right metallicity, meaning enough heavy elements to form rocky planets. You need the star to be stable over billions of years, without huge flares or dramatic changes in brightness. You need the planet to have the right mass, big enough to hold an atmosphere and keep a hot core for plate tectonics, but not so big that it turns into a mini Neptune with a thick gas envelope. You need water delivery, but not too much. You need plate tectonics to cycle carbon and regulate climate. You may need a big moon to stabilize tilt. You probably benefit from outer giant planets in the right positions to manage impact rates. Even if you rate each of those as only a 1 in 10 filter, the combined effect is brutal. 1 in 10 stars has the right metallicity. 1 in 10 with that metallicity has the right stability. 1 in 10 of those has a planet in the habitable zone. 1 in 10 of those planets has the right mass and composition. Multiply that kind of chain a few times and you're already at a 1 in 10,000 or 1 in a million outcome. And that's before you even talk about life actually starting, surviving, and becoming complex. The scary possibility is that Earth sits in a very small target zone in this big parameter space. Outside that zone, you still have planets, but most of them are dead rocks, scorched worlds, gas-wrapped super-Earths, tidally locked extremes, or frozen outposts. They might have interesting chemistry, they might even have simple life in some cases, but the full package, long-term liquid water, a stable climate, a solid surface, plate tectonics, and protection from constant disaster could be rare. So instead of a galaxy full of Earth twins, you might have a galaxy full of worlds that almost made it, or never had a chance. The habitable universe becomes not everywhere, but more like a thin scatter of lucky cases inside a huge population of sterile or hostile environments. Now put that against the earlier layers of emptiness. Most of space is vacuum. Matter is confined to thin filaments and islands. Inside those islands, only certain galactic regions are calm enough. Inside those regions, only some stars have the right planets. And inside those systems, only a small subset of planets may meet all the conditions Earth meets. You keep shrinking the real estate where complex life can plausibly show up and survive. That leads straight to the next uncomfortable question. If there are hundreds of billions of stars and probably hundreds of billions of planets, and at least some subset of those planets are roughly Earth-like, where are all the other civilizations? Why is the sky so quiet? Why do our instruments pick up nothing but natural signals if the universe has had billions of years and so many chances to build someone else? With hundreds of billions of stars in your galaxy and hundreds of billions of galaxies in the observable universe, the cosmos should be loud by now. You should see obvious signs of engineering, hear artificial signals, notice galaxies that look tampered with. Instead, when you actually look and listen, you get almost nothing. The universe feels not just empty of matter, but empty of company. This is the core of the Great Silence, and it starts with a simple question asked at a lunch table. Enrico Fermi, a physicist at Los Alamos in the 1950s, was talking with colleagues about aliens. They were tossing around the usual ideas, lots of stars, lots of planets, big timescales. At some point, Fermi just cut through all of it with one sentence. Where is everybody? His logic is straightforward. If technological civilizations arise even on a tiny fraction of habitable worlds, and if they survive for long enough to learn how to travel or send probes, then over millions or billions of years they should spread. Not instantly, not filling every square inch, but enough to leave traces. Star systems with obvious engineering, energy use on massive scales, signals bouncing between colonies. After billions of years, the Milky Way should not look untouched. But your observations do not match that expectation. You point radio telescopes at the sky, you scan for narrowband signals, you look for patterns shouting artificial, and you get only noise. You search for stars that are dim in visible light but glowing in infrared, the kind of thing you might expect from huge energy harvesting structures, and you do not see any obvious galaxy-wide projects. On the largest scales, the universe looks natural, untouched, and quiet. Take their radio searches first. Projects grouped under the name SETI, the Search for Extraterrestrial Intelligence, have spent decades listening to the sky, especially at frequencies that make sense for communication, like around the hydrogen line. The idea is that a technological civilization, using radio for beacons or communication, might leak or deliberately broadcast signals into space, and that some of those signals would stand out from natural backgrounds. Modern radio telescopes are sensitive enough that if a civilization with technology similar to ours aimed a powerful narrow-band radio beam at us from many light years away, we could detect it. We would see a spike in frequency, a signal that does not match natural emission lines, something clearly engineered. We have scanned big chunks of sky across many frequencies at many times. So far, the result is basically negative. There have been a few weird blips, like the famous wow signal, but nothing repeatable, nothing stable, nothing that holds up as a clear, persistent technosignature. If the galaxy is full of civilizations shouting across the void with radio beams, they are either missing us completely, turned off, or not there in large numbers. Maybe, you say, advanced civilizations do not use radio for long, or they go quiet, or they use more subtle channels. That is possible, so astronomers looked for a different kind of footprint, waste heat from massive engineering. If you build something like a Dyson sphere, a structure around the star that captures most of its energy output, you don't get to use that energy perfectly. You always end up dumping some fraction of it back into space as waste heat. That waste heat would show up in the mid-infrared part of the spectrum. Infrared surveys like WISE have mapped the sky at those wavelengths, and you can search for stars or even entire galaxies that are unusually bright in infrared compared to their visible light, the kind of thing you would expect if a lot of their starlight is being captured and re-radiated as heat. Again, the answer is not encouraging for the crowded universe view. You don't see clear populations of Dyson spheres. You don't see galaxies where a significant fraction of stars look artificially wrapped. That doesn't prove there are no advanced civilizations, but it does say this. If they exist, they are extremely rare, extremely efficient and quiet, or they stay at scales far below what your current surveys can see. That brings you to the really uncomfortable possibility. Your own Milky Way might be empty of other technological civilizations right now. Not empty of bacteria-like life, that's still an open question, but empty of anyone building radios, telescopes, or large-scale machines. The distance between truly habitable systems, plus the time it takes to evolve intelligence, plus the risk of self-destruction, might mean that at any given time there are only a few, or even zero, active technological species in a whole galaxy like this. On human scales, that's hard to feel. You're used to thinking of a deserted area as a few miles of empty land. Here, deserted might mean tens of thousands of light years between technological peaks, or simply no other peaks at all. When you put that against the size of the galaxy, you realize how easy it is to have a universe that feels full of potential on paper, but is practically silent in reality. So the Great Silence isn't just about vacuum, it's about a social vacuum, a communication vacuum. You look out across billions of light years and you don't see obvious signatures of minds at work. You listen across a wide range of radio and optical frequencies, and you hear mostly natural processes. If there are other civilizations, they are either hiding extremely well, have lifetimes so short that almost none overlap with yours, or they are so rare that you simply don't share a galaxy with them. And that pushes you towards a harsher explanation. Maybe the universe isn't just unlucky. Maybe something in its physics and history is actively cutting down almost every attempt at complex technological life. Maybe there are great filters before intelligence and after, points in the chain where most worlds fail and almost none make it through. If that's true, then the emptiness you see isn't just distance and vacuum. It's the result of a process that kills almost every branch that tries to climb to your level and above. Maybe the universe isn't empty just because it got unlucky. Maybe its own physics is set up to kill almost every attempt at complexity before it can spread. When you line up all the steps needed to go from a hot early universe to a technological civilization, you don't see one hard step, you see a whole series of filters, each one knocking out most candidates. Start at the very beginning, before life. The early universe was not friendly. Radiation levels were high, galaxies were small and unstable, collisions and violent events were common. On top of that, the basic chemistry was wrong. Right after the Big Bang, you mostly had hydrogen and helium with a trace of a few light elements. No carbon, no oxygen, no silicon, no iron. Those heavier elements, the ones you need for rocks, planets, and biochemistry, had to be forged inside stars and spread by supernovae. That means you needed multiple generations of stars to live and die before you could even build a planet like Earth. For billions of years after the Big Bang, nothing like your world could exist anywhere, not because nobody tried, but because the periodic table in real objects just wasn't rich enough yet. Early galaxies also had more star formation and more violent events, including more gamma-ray bursts and more active black holes. Even if simple chemistry started somewhere, it was living under a sky that hit it hard and often. So the first filter is simple. The universe had to cool down, enrich itself with heavy elements, and calm down enough on large scales before the building blocks for Earth-level planets were even available. For a huge span of cosmic time, complex life was off the table by basic nucleosynthesis alone. Now move to the next stage. You finally get rocky planets, liquid water, and calmer galaxies. Does life automatically climb toward complexity? Not obviously. On Earth, life appears early in the record, but it stays simple for a very long time. The first signs of life go back more than 3.5 billion years. Multicellular animals with nervous systems show up only in the last few 100 million years. That is a gap of billions of years where life is mostly single-celled and microscopic. To get from cells to animals, you need long periods of planetary stability. You need the climate to stay inside a certain range. You need the atmosphere to be maintained. You need energy sources to be steady enough. Large asteroid impacts, volcanic supereruptions, extreme climate swings, all of these can reset or slow down complexity. Earth's history includes several mass extinctions, big hits that reshaped ecosystems. It is not hard to imagine worlds where the reset button gets hit more often, so complexity starts climbing and then keeps getting knocked back to simple forms. So there is a before intelligence filter. Life might start often, but complex multicellular life that survives long enough to diversify into large, active organisms might be rare. A planet can be full of microbes for billions of years and never get beyond that because it never gets a long enough quiet stretch. Then there is another filter. Even with complex life, intelligence capable of technology might be rare. On Earth, for most of its history, the planet was full of complex animals with no interest in building tools beyond what their bodies provided. Dinosaurs ruled for tens of millions of years with no sign of technology. Large-brained primates appear late. Only one small branch, your branch, built radios and rockets. Many ecosystems can settle into stable configurations without any strong pressure to develop high intelligence. A world dominated by successful herbivores and carnivores that are well adapted to their niches has no built-in drive to produce a species that worries about mathematics. Intelligence is expensive in energy. It requires complex brains and long childhoods. If a planet does not reward that investment, evolution will not push that way. So even on planets with forests and oceans and complex food webs, you might never get a species that does astronomy, develops physics, or manipulates electricity. They might have rich biospheres and no technology, ever. That is a before technology filter. Now assume you pass all of that. You get a technological civilization. You build industry, global networks, powerful tools, and eventually you learn how to manipulate your own biology and your own environment. At that point, a new set of filters appears, and they're fast compared to cosmic time. Once you control nuclear energy, you can wipe yourself out in hours. Once you can engineer pathogens, you can build diseases more dangerous than anything natural evolution came up with. Once you build artificial intelligence and autonomous systems, you hand more and more control to things you might not fully understand. Once you change your planet's climate on a global scale, you risk destabilizing the same environment that enabled your rise. On cosmic timescales, a few hundred years of technological missteps is nothing. It doesn't take much time compared to the age of a galaxy for a civilization to ruin its own biosphere, deplete its resources, or trigger a war or cascade of failures that ends its run. If most technological species do not manage to stabilize their use of power, most of them do not last long. They flare up briefly, then vanish. Put these filters in a row and the great silence stops being surprising. You have filters before life, making heavy elements and calm galaxies, filters before intelligence, requiring billions of years of stable conditions for complex life, filters before technology, requiring a rare jump to tool-using, symbol-using brains, filters after technology, where self-inflicted disasters can end the story quickly. If each of those has a decent chance of failure, the combined probability of making it all the way through and then staying around long enough to fill a galaxy gets tiny. The emptiness of the sky might simply be statistics from a deadly process. Almost every attempt to climb the ladder falls off before it can build galaxy-spanning projects or sustained beacons. You see no super civilizations not because the universe cannot host them in principle, but because almost none ever survive long enough. And remember, all of this is happening in a universe that is already physically draining. Dark energy is pushing galaxies apart, star formation is fading, and the long-term trend is toward lower density and less structure. On top of that, there's another slow process running in the background, one that takes matter out of circulation and locks it into places where nothing can escape. As time goes on, more and more of the universe's content is getting trapped in black holes, compact objects where gravity is so strong that not even light can get out. If you want to see how far this emptiness trend goes, you have to follow matter all the way down into those final sinks. As time goes on, more and more of the universe's matter is getting locked into regions that nothing can escape from. The longer the cosmos runs, the more of its interesting stuff ends up inside black holes, where it basically stops participating in everything else. Start with the small ones, the stellar mass black holes. When a star much more massive than the Sun reaches its end of life, its core collapses. If that core is heavy enough, the collapse doesn't stop at a neutron star. Gravity wins completely, and you get a black hole a few times the mass of the Sun. The event horizon of something like that, the surface beyond which not even light can escape, can be only a few dozen miles across. So you have multiple solar masses of matter that used to be spread out over a star hundreds of thousands of miles wide, crushed into a volume the size of a city. That mass still curves space, still exerts gravity, still orbits inside galaxies. But whatever falls inside that boundary is gone to the outside universe. No light, no signals, no matter comes back out. Over billions of years, normal stellar evolution keeps converting regular stars into compact remnants, white dwarfs, neutron stars, and black holes. Big stars die quickly and leave black holes. Smaller stars leave white dwarfs that can later be pushed over the limit and collapse. Neutron stars can merge and form bigger black holes. Bit by bit, a decent chunk of a galaxy's mass is moved from bright, extended stars into tiny, dark remnants. Now look at the centers of galaxies. Observations show that almost every large galaxy has a supermassive black hole sitting in its core. These are monsters with millions or even billions of times the Sun's mass, squeezed into a region smaller than the solar system. They don't just sit there passively, they grow. Supermassive black holes gain mass in two main ways: by swallowing gas and stars from their surroundings and by merging with other black holes when galaxies collide. Each time two galaxies merge, their central black holes gradually sink toward the new common center and eventually coalesce. Over cosmic time, that builds up a few very massive objects that dominate the central gravity. In dense environments, like big galaxy clusters, these central black holes can become some of the largest single mass concentrations around. They're like anchors at the bottom of a potential well. Matter falls toward them, and if it gets too close, it doesn't come back. The story gets worse when you look at how black holes feed. When gas falls in, it does not usually drop straight down. It forms a hot, spinning disk around the black hole, an accretion disk. Friction and magnetic fields in that disk heat the gas to extreme temperatures and can launch narrow, powerful jets of particles far out into space at speeds close to the speed of light. Those jets and the radiation from the accretion disk dump energy into the surrounding galaxy and its halo. They can blow gas out of the central regions, heat it up, and push it into intergalactic space. Once that gas is dilute and hot, it is very hard for it to cool back down and fall into dense, star-forming clouds. So black holes are doing two things at once, locking away matter they actually swallow and sabotaging the fuel supply that galaxies need to make new stars. So as time passes, more matter ends up in compact remnants, especially black holes, and less matter remains in the cool, dense form that can build new structure. Star formation slows. Big galaxies go red and dead, and the mass budget shifts toward dark, compact objects and thin gas. Now, take this to the extreme future. Fast forward trillions of years, far beyond the current age of the universe. Most normal stars, like the Sun, will be gone. Low-mass red dwarfs will still be burning, but eventually even they will use up their fuel. White dwarfs will cool into cold, dark remnants. Neutron stars and black holes will keep orbiting in slowly thinning galaxies. At that stage, black holes are some of the last massive structures left that still have strong gravity. They will continue to merge when orbits bring them together, building fewer but larger holes. A lot of the matter that once made up bright stars, planets, moons, and everything on their surfaces will now be trapped behind event horizons, compressed into regions where space and time are warped almost beyond recognition. Even black holes are not permanent, though. Quantum effects predict a process called Hawking radiation, where black holes very slowly lose mass by emitting tiny amounts of radiation. For stellar and supermassive black holes, this evaporation is incredibly slow, taking far longer than the current age of the universe. But over absurdly long timescales, they will shrink and eventually disappear. By the time that happens, the universe will be almost pure emptiness, with a thin haze of low-energy particles and photons spread over a vast volume. The matter that used to be arranged into galaxies, stars, planets, moons, and everything on their surfaces will now be trapped behind event horizons, compressed into regions where space and time are warped almost beyond recognition. In other words, the universe is literally folding its matter into fewer and fewer storage bins, then very slowly dumping those bins out into a featureless background. The trend is away from variety and structure and toward uniform, thin nothing. That raises the next step in the chain. If black holes are the last big actors, and even they eventually evaporate, what does that say about the overall direction of the universe? Is there any kind of reset, any chance of new structure, or is everything sliding one way toward a final, boring end state where nothing interesting can ever happen again? Physics gives you a built-in direction, from order to disorder, from useful energy to useless heat. On human scales, that means things rust, batteries drain, coffee cools. On cosmic scales, that same direction points to a very specific endgame, and it is not a giant explosion. It is something much slower and much more boring. A universe that slides into almost perfect nothing and then stays there. The key idea is entropy. In simple terms, entropy measures how spread out and disorganized energy is. The second law of thermodynamics says that in a closed system, entropy tends to increase. You can locally decrease it for a while, like organizing your room, but only by increasing it somewhere else, like burning energy in your body. Overall, the total trend is one way. Now here's the weird part. The early universe, right after the Big Bang, was hot, dense, and very uniform. Same temperature almost everywhere, small fluctuations, not a lot of obvious structure. In some senses, that looks like high entropy. Everything's smeared out. But gravity complicates that picture. A uniform block of matter under gravity is actually low entropy compared to a clumpy one, because there are many more ways to arrange matter into collapsed structures than there are to keep it perfectly even. So as the universe expanded and cooled, gravity started to amplify those tiny initial ripples, pulling matter together into gas clouds, stars, and galaxies. That created local pockets of low entropy, like stars and planets, at the cost of increasing entropy overall. Radiation from these structures, plus all the mess of collisions and shocks, spread energy out. The second law still wins, but it allows temporary islands of order to form on the way. Stars are one of the main engines in this process. They exist because there's a temperature difference between their cores and the cold background of space. Nuclear fusion in the core releases energy, and that energy flows outward, eventually radiating away as light and heat. As that radiation spreads into space, it helps equalize temperature differences between hot regions and cold regions. Every time a star shines, entropy goes up. The star is turning concentrated nuclear fuel into diffuse radiation. Planets, like Earth, can temporarily use that energy flow to build complex structures, like life, but they do it while dumping waste heat back out, raising entropy overall. Over billions of years, as stars burn their fuel, they reduce the number of big temperature gradients left to exploit. The story gets worse when you look at how black holes feed. When gas falls in, it does not usually drop straight down. It forms a hot, spinning disk around the black hole, an accretion disk. Friction and magnetic fields in that disk heat the gas to extreme temperatures and can launch narrow, powerful jets of particles far out into space at speeds close to the speed of light. Those jets and the radiation from the accretion disk dump energy into the surrounding galaxy and its halo. They can blow gas out of the central regions, heat it up, and push it into intergalactic space. Once that gas is dilute and hot, it is very hard for it to cool back down and fall into dense star-forming clouds. So black holes are doing two things at once, locking away matter they actually swallow and sabotaging the fuel supply that galaxies need to make new stars. So, as time passes, more matter ends up in compact remnants, especially black holes, and less matter remains in the cool, dense form that can build new structure. Star formation slows, big galaxies go red and dead, and the mass budget shifts toward dark, compact objects and thin gas. Now, take this to the extreme future. Fast forward trillions of years, far beyond the current age of the universe. Most normal stars, like the Sun, will be gone. Low-mass red dwarfs will still be burning, but eventually even they will use up their fuel. White dwarfs will cool into cold, dark remnants. Neutron stars and black holes will keep orbiting in slowly thinning galaxies. At that stage, black holes are some of the last massive structures left that still have strong gravity. They will continue to merge when orbits bring them together, building fewer but larger holes. A lot of the matter that once made up bright stars, planets, moons, and everything on their surfaces will now be trapped behind event horizons, compressed into regions where space and time are warped almost beyond recognition. Even black holes are not permanent, though. Quantum effects predict a process called Hawking radiation, where black holes very slowly lose mass by emitting tiny amounts of radiation. For stellar and supermassive black holes, this evaporation is incredibly slow, taking far longer than the current age of the universe. But over absurdly long timescales, they will shrink and eventually disappear. By the time that happens, the universe will be almost pure emptiness, with a thin haze of low-energy particles and photons spread over a vast volume. The matter that used to be arranged into galaxies, stars, planets, oceans, and living things will have spent a huge fraction of its final history locked in tiny, compact regions, and then finally leaked out as faint radiation into a nearly perfect vacuum. In other words, the universe is literally folding its matter into fewer and fewer storage bins, then very slowly dumping those bins out into a featureless background. The trend is away from variety and structure and toward uniform, thin nothing. That raises the next step in the chain. If black holes are the last big actors, and even they eventually evaporate, what does that say about the overall direction of the universe? Is there any kind of reset? Any chance of new structure? Or is everything sliding one way, toward a final, boring end state where nothing interesting can ever happen again? Physics gives you a built-in direction, from order to disorder, from useful energy to useless heat. On human scales, that means things rust, batteries drain, coffee cools. On cosmic scales, that same direction points to a very specific endgame, and it is not a giant explosion. It is something much slower and much more boring, a universe that slides into almost perfect nothing and then stays there. The key idea is entropy. In simple terms, entropy measures how spread out and disorganized energy is. The second law of thermodynamics says that in a closed system, entropy tends to increase. You can locally decrease it for a while, like organizing your room, but only by increasing it somewhere else, like burning energy in your body. Overall, the total trend is one way. Now, here's the weird part. The early universe, right after the Big Bang, was hot, dense, and very uniform. Same temperature almost everywhere. Small fluctuations, not a lot of obvious structure. In some senses, that looks like high entropy. Everything's smeared out. But gravity complicates that picture. A uniform block of matter under gravity is actually low entropy compared to a clumpy one, because there are many more ways to arrange matter into collapsed structures than there are to keep it perfectly even. So as the universe expanded and cooled, gravity started to amplify those tiny initial ripples, pulling matter together into gas clouds, stars, and galaxies. That created local pockets of low entropy, like stars and planets, at the cost of increasing entropy overall. Radiation from these structures, plus all the mess of collisions and shocks, spread energy out. The second law still wins, but it allows temporary islands of order to form on the way. Stars are one of the main engines in this process. They exist because there's a temperature difference between their cores and the cold background of space. Nuclear fusion in the core releases energy, and that energy flows outward, eventually radiating away as light and heat. As that radiation spreads into space, it helps equalize temperature differences between hot regions and cold regions. Every time a star shines, entropy goes up. The star is turning concentrated nuclear fuel into diffuse radiation. Planets like Earth can temporarily use that energy flow to build complex structures, like life, but they do it while dumping waste heat back out, raising entropy overall. Over billions of years, as stars burn their fuel, they reduce the number of big temperature gradients left to exploit. This process does not run forever at the same pace. Stars have lifetimes. Big, bright stars burn out quickly. Smaller stars live longer, but they also eventually exhaust their fuel. As time passes, the rate at which stars form drops, as you already saw, and the rate at which new gradients are created drops too. The universe gets fewer new engines and more cooling embers. Now plug this into the long-term picture, the heat death scenario. Assume dark energy keeps doing what it is doing now, driving accelerated expansion. The universe keeps getting bigger, matter gets more and more spread out, galaxies stop forming new stars, existing stars age and die, white dwarfs cool, neutron stars and black holes dominate, then black holes themselves slowly evaporate via Hawking radiation. In that far future, the temperature of space everywhere drops closer and closer to absolute zero, but never quite reaches it. You end up with a very thin fog of low-energy photons and elementary particles spread over an enormous volume. The important point is not just that it is cold, it is that the temperature is almost the same everywhere. There are no big differences to exploit, no hot cores with cold surroundings, no easy way to set up engines, biological or mechanical, that can feed on gradients. Without gradients, you do not have usable energy. You still have energy in an absolute sense, but it is all smeared out in a way that cannot do work. It's like having money evenly distributed as dust across a continent. Technically, it is there, but you cannot pick it up and spend it. Complex processes like life and thinking and technology rely on constant energy flow from a hotter source to a colder sink. Take away the differences, and those processes cannot run. So the heat death is not fire, not a big final blast. It is a slow flattening of all the differences that make anything interesting possible. No new stars, no new galaxies, no new chemistry beyond low-level reactions. Just occasional interactions in a nearly uniform, almost frozen background. That is what maximum entropy looks like on a cosmic scale. It's not dramatic, it's just done. The universe is not only empty of galaxies and bright stars, it's empty of any realistic path to build them again. The distribution of matter and energy has already explored the space of possibilities allowed by the laws of physics, and has settled into the most probable, most boring configuration. And here's the part that should really land. This is not just one possible outcome among many. As far as we can tell, this is where the same laws that allow you to exist are pushing everything. The second law of thermodynamics does not turn off. Gravity, star formation, black hole growth, all of it fits into a story where low entropy pockets appear, briefly, in a universe that is drifting toward a state where nothing like you can ever appear again. So, cosmic emptiness is not just what you see when you look between the galaxies today. It's the final product. The end state is not a universe that is just empty, it's a universe that is empty in a way that cannot be reversed, with no fuel, no gradients, no escape route back into complexity. That brings up a very sharp question. If the rules of the universe drive everything toward this dead, flat state, how is it that those same rules also allowed even a short window where complex life, and then technology, and then you, could exist at all? Why do the numbers land in the narrow range where the universe is lethal in the long run, but just barely supportive in the short run? Here's the twist you've been walking toward the whole time. The universe is terrifyingly empty, and that is probably the only reason you're here to complain about it. The same things that make the cosmos feel hostile and bleak are exactly what bought you the time and stability you needed. Start with a simple counterfactual. Suppose the universe had a lot more matter in it. Same basic laws, just more stuff per cubic yard. Gravity would be stronger on large scales. Expansion after the Big Bang would slow down faster, maybe even reverse. In the most extreme cases, the universe could recollapse long before stars have had time to live and die and build heavy elements. You would get a brief bright era and then a crunch. Even if it did not recollapse, a denser universe would form structures differently. More matter means clumps grow faster and more violently. Black holes would form more easily. Regions would collapse into super dense objects instead of forming nice, long-lived galaxies with well-spaced stars. Stellar encounters would be more common. Orbits would be less stable. You would get fewer quiet, billion-year-long windows where a small rocky planet can orbit at a comfortable distance without being thrown out or fried. So the low average density, the thin spread of matter, is not just a visual detail. It's the thing that stops gravity from collapsing everything too quickly. Emptiness buys you time. It lets galaxies form slowly, lets stars live billions of years, and gives planets stable orbits long enough for evolution to run its long, messy experiment. Now, zoom in on the numbers. The universe is controlled by a set of parameters like the density of matter, the amount of dark energy, the strength of gravity, the relative strengths of forces. When cosmologists run the equations and then nudge those numbers, they find that there is a surprisingly narrow range that gives you a universe anything like this one. If you crank up dark energy a lot, the universe starts accelerating too early. Matter gets pulled apart before it can clump into galaxies. You end up with a very smooth, very empty universe, but now with almost no stars or planets at all. If you dial dark energy far down or make it negative, gravity can win too hard. Structures can collapse and merge and maybe recollapse the whole thing in a big crunch before complex life can appear. The same with gravity itself. Make gravity much stronger and everything collapses quickly into black holes and dense clusters. Make it much weaker and matter barely clumps at all. You might get diffuse gas and small, weak structures, but not the kind of dense stars and galaxies you need to cook heavy elements and build complex chemistry. Other parameters, like the ratio of matter to radiation in the early universe, the amplitude of the first density ripples, and so on, all land in ranges that allow both structure and long-term stability. So you end up with this uncomfortable picture. The key cosmological numbers are not sitting at random values. They sit in ranges where you get a universe that forms galaxies and stars, but not so fast that everything collapses and not so slow that nothing forms. They look weirdly just right for a universe that is mostly empty but still has rare islands where complexity can grow. This is what people call fine-tuning. You do not have a proof that they must be this way. You just notice that if they were very different, either you get a dead universe with no structure or a universe that collapses or tears itself apart too fast. The actual values sit in the middle where observers like you can exist. Anthropic reasoning is one way to deal with that. The anthropic principle sounds almost trivial when you first hear it. Of course you observe a universe that allows your existence. You could not exist in one that did not. That seems like a tautology, but it has a bite. It says you should expect your observed universe to be just barely good enough for observers, not wildly overbuilt for comfort. If there are many possible universes or many regions with different parameters, observers will only ever find themselves in the ones that permit observers. In that picture, it is no surprise that your universe feels finely balanced and slightly hostile. It does not have to be nice, it just has to be non-lethal long enough for somebody to evolve who can ask questions. So from that angle, an almost completely empty universe is exactly what you should expect. Too much matter and you die in a collapse or in a mess of black holes. Too much dark energy and you never get galaxies. Too much activity and radiation kills complex life everywhere. The sweet spot is a universe that is mostly nothing with a few fragile temporary structures that barely hang together and occasionally host life. That means the emptiness you see is not a bug, it is a selection effect. Of all the ways a universe could have turned out, the ones that produce observers will usually be the ones that look narrowly tuned and weirdly empty, because those are the ones where life can sit quietly for billions of years and evolve complex brains. Here's the creepy implication. You are not living in a universe that wants life. You're living in a universe whose parameters accidentally allow small pockets of life-supporting structure in between huge stretches of lethal conditions. You're experiencing it from one of those pockets, so it feels like the universe is about you, but the big picture says otherwise. The universe does not owe you density. It does not owe you neighbors. It does not owe you future options. Emptiness is the baseline. The rare, brief deviation from emptiness, the bit where galaxies form, stars shine, planets cool, and chemistry gets complicated enough to produce minds, that is the exception. You. So the question shifts. It is no longer why is the universe so empty, as if emptiness needs an excuse. The sharper question is, how is there anything here at all, given how strongly everything is tilted toward either simple uniformity or catastrophic collapse? And that leads into one more layer of discomfort. If you know that you can only exist in a tiny subset of places and times, then all your measurements are biased. You are automatically living in an unusually comfortable corner of an uncomfortable universe, at an unusually favorable moment in its history. The universe you can infer from your viewpoint is not a typical sample. It is the least bad patch you could possibly wake up in. Statistically, you are always going to wake up in one of the rare, non-empty patches of the universe. That does not mean the rest of it is anything like you see. Your whole view is biased by the simple fact that if a region cannot support observers, nobody there is going to complain about it. This is observer bias in its raw form. You can only exist in a place that allows complex chemistry, long-lived stars, and stable planets. That means every measurement you make, like how dense matter feels, how common habitable planets seem, and how normal your environment looks, is already conditioned on being in a non-typical patch. You are not pulling a random sample from the entire universe. You are pulling a sample from the subset of regions that did not instantly kill off the possibility of you existing. So, when you look around and see a galaxy with plenty of stars, a sky with at least some structure, and a planet that has liquid water and an atmosphere, you are not seeing what the average point in space looks like. You're seeing what the least bad points look like, because those are the only ones that can host witnesses. The universe as a whole can be far emptier, far more hostile, and you would never know it directly, because no one is taking measurements from those places. Now, put that together with the cosmic web. On the largest scales, matter lives in thin filaments and nodes, with gigantic voids in between. Life, as far as we can tell, needs stars, heavy elements, and relatively dense gas to form planets. Those things exist in the filaments and clusters, not in the voids. So any observer that appears anywhere in the universe will by definition be sitting in one of those thin structures, not drifting alone in the middle of a 300 million light-year hole. That gives you a lucky filament effect. You are guaranteed to live on or near one of the rare threads of matter. From your perspective, you look left, you see galaxies. You look right, you see galaxies. You run simulations, you see a universe with lots of structure. It's easy to think, this is what the universe is like. But pull back and include all the empty volume in between filaments, and you realize most of space is not like your neighborhood at all. You are in the bright lines on the map. Most of the map is blank. So you have spatial selection, but you also have temporal selection. You are not born at a random time in the universe's history. You can only arise after a few key things have happened and before other key things shut the game down. First, you need enough heavy elements to build rocky planets and complex chemistry. That requires multiple generations of stars to live and die, so you can't show up too early. Second, you need evolution to run for billions of years on a stable world. That takes more time. Third, you need the universe to still have strong energy gradients, stars still shining, temperatures not all equalized. That means you can't show up too late when star formation has almost stopped and everything is cooling toward uniformity. Put those constraints together and they naturally point to a window. A few billion years after the peak of star formation, when galaxies have built up heavy elements but are still forming some new stars. Long before the heat death, while stars are still common and black holes have not scooped up most of the mass. That sweet spot is roughly where you are right now, about 13.8 billion years after the Big Bang. So of course you are not seeing the universe at a random age. You are seeing it at a time when it is at maximum interestingness for life, with a decent mix of old stars and new stars, a rich chemical inventory, and plenty of energy flows. From your point of view, the universe looks just active enough to be exciting and just calm enough to be survivable. But that is not a coincidence. That is a selection effect. Now, think about what this does to your picture of the whole story. Right now, with big telescopes and multiple wavelengths, you can see the cosmic web. You can detect the afterglow of the Big Bang. You can measure the expansion of the universe and infer dark energy. You can see that your galaxy is one of many, linked into a larger structure. But go forward trillions of years. In that far future, any observers that still exist will be sitting in a universe where dark energy has pushed almost all other galaxies beyond the event horizon. Only their local group, or whatever remnant it has merged into, will remain visible. The cosmic microwave background will be so redshifted and diluted that it is effectively undetectable. The maps of large-scale structure will be gone. No obvious traces of the Big Bang will be left in the data they can collect. From their perspective, the universe will look even emptier than it does to you. They might see only one big galaxy, surrounded by blackness. They will have no direct evidence that there were ever other galaxies, no direct sign of the cosmic web, no clean handle on expansion. For them, cosmology will be almost impossible. Their best theories might say this is all there is, and they will be wrong, but they will have no way to prove it. Your current view, which already feels like a nearly empty universe, is actually unusually rich. You live at a time when you can still see the web, still measure the background radiation, still notice that you are in a filament inside a much larger structure. You are wedged into a narrow era where the universe is still revealing its history to you, before it hides most of that history behind horizons and redshift. So when you put all these selection effects together, you get a harsh conclusion. The universe you can reconstruct from your vantage point is one where emptiness dominates. Structure is rare, and your position is not typical. You are in one of the least boring corners of a mostly boring universe during one of the least boring intervals of a very long, mostly quiet timeline. And that sets up the final turn. If the only reason you are here is that the universe happens to be this empty and this tuned, and you happen to be in this specific filament in this specific window, what does that say about your situation? Is this emptiness just background flavor, or is it the price you pay for existing at all and the warning that your window is going to close? You live in a universe that is almost completely nothing, and that is not a bug in the design. That is a condition for you to exist at all, and the warning label that this situation does not last. Step back and recap what you are actually sitting in. Take a cube of space, a yard on each side, out between galaxies. On average, that cube has maybe a few lonely atoms in it. Not molecules, not dust, just single atoms drifting through a volume that, for all practical purposes, is vacuum. Compare that to a cubic yard of air in your room, packed with something like 10 million trillion molecules bouncing off each other. Your normal, everyday empty feels like a crowded stadium compared to the true average density of the universe. Matter is not spread out evenly. It is concentrated into thin filaments and little islands, galaxies and clusters, connected in a giant cosmic web. Between those threads, you have voids hundreds of millions of light years across, regions where almost nothing lives, and those voids make up most of the volume. If you could pick a random location in the cosmos, you would almost certainly land in one of those dead zones, far from any stars, with nothing nearby for unimaginable distances. On top of that, you have dark energy, the invisible term in the equations that accelerate the expansion of space. It's steadily pushing galaxies away from each other, faster and faster, turning each gravitationally bound group into an isolated prison. Over time, those prisons lose contact. No signals, no travel, no shared history. Just local islands drifting apart in a sea that's getting darker and more empty with every passing billion years. Now, here's the twist. That emptiness is also your life support. If the universe were much denser, gravity would have crushed everything together quickly. You wouldn't get nice, well-spaced galaxies. You'd get a fast collapse into clusters and black holes. Long-lived stars like the sun would struggle to form or survive. Planetary orbits would be unstable, constantly kicked and scrambled by close encounters. Instead of billions of years of slow evolution, you'd get violent rearrangements on short timescales. The low density lets galaxies assemble slowly over billions of years instead of in one catastrophic rush. The space between stars means your solar system can sit in a relatively quiet pocket without constant direct hits from neighbors. You need a certain amount of nothing between stars so that planets can orbit safely, so that radiation from supernovas and gamma-ray bursts is infrequent enough that life has a chance to recover when it gets hit. Even the night sky does you a favor. If the sky were as bright as the surface of a star in every direction, you wouldn't have a cold background to dump heat into. The energy flows that life depends on need a hot source and the cold sink, a star above and cold space around. The darkness gives you that sink. Long cosmic timescales, made possible by low density and expansion, give evolution room to experiment, fail, and try again. So the emptiness around you is doing two jobs at once. It keeps the universe from collapsing too fast, and it gives you a thin margin between all the dangerous processes running in stars and galaxies. It's the thin margin that lets a planet like Earth sit quietly enough, long enough for complex chemistry and biological evolution to happen. But there is no way to spin this into a happy ending, because the same mechanisms that gave you breathing room are the ones that are shutting the window. The expansion that stops the sky from turning into a wall of fire is the same expansion that is pushing most galaxies out of your reach and eventually out of your view. The dark energy that prevents recollapse is the same dark energy that will lock your local group into a permanent island and erase the rest of the cosmic web from your future. The emptiness that reduces collisions and keeps orbits stable also means that once material is used up or locked in black holes, there's not much left to rebuild with. Star formation is already past its peak. The universe is not ramping up, it is winding down. Each galaxy is using or losing its cold gas. Black holes and feedback are heating and expelling fuel. The rate of new stars, and therefore new planets, is dropping. At the same time, entropy is creeping upward. Every second, stars radiate energy out into space, flattening temperature differences. Every second, usable energy is being converted into lower-grade heat. On long timescales, all of this points in one direction. Complexity is temporary. You get an early universe that is too simple, too hot, too uniform. Then a middle era, the one you are in, where gradients are strong, structure is rich, and there is just enough time and calm for life to appear. And then a late universe, thin, cold, and dominated by dead remnants, where there's almost no free energy left to power anything like you. From that perspective, everything you care about, stars, galaxies, planets, life, culture, technology, sits on a narrow ridge between two oceans of nothing, the nothing before structure and the nothing after heat death. The ridge is high compared to those oceans, but it is short. So what do you do with that? You are alive in a rare era, on a rare type of planet, in a relatively calm part of a galaxy, in a thin filament of matter, in a universe that is otherwise mostly vacuum, radiation, and silence. You are one of the very few configurations of particles where the universe has become able to look back at itself and ask, why is it like this? From the universe's point of view, that question is almost beside the point. The laws do not care if they produce observers or not. They simply run. They produce a mostly empty universe with sparse islands because that is what those numbers do. Inside one of those islands, under one star, on one small rock, chemistry managed to build something that can notice the emptiness and feel weird about it. That is the real horror. Not just that the universe is empty, but that for a tiny span of time, it is not quite empty enough, and that slight deviation is enough to produce you and every question you have about meaning, purpose, and future. You are the byproduct of a narrow, unstable balance that will not last. So zoom out one last time. Start at your body, made of atoms that were forged in dead stars. Pull back to the room you are in, the city, the continent, the whole Earth, a small ball 8,000 miles wide. Pull back to the solar system, with its planets scattered across billions of miles of mostly empty space. Pull back to the Milky Way, a disk 100,000 light-years across, with the sun as just one faint dot in a spiral arm. Pull back farther to the thin filament of the cosmic web that holds that group, stretched between vast voids hundreds of millions of light-years across. And then pull back until even that filament is just one faint line in a universe that is mostly dark, mostly silent, and getting emptier with time. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.